You may have noticed that our three-step process for finding the intersection line of two planes is usually a pretty good system, but sometimes there's a dilemma. So when we substitute a number like 0 in for both equations and solve the resulting system, sometimes it doesn't work. So I gave some situations. If the planes are the same, the planes are parallel, or the line is parallel to the xy, yz, or xz plane, this won't work. And so let's break down some of those cases even more. An example of when your choice of a value, typically we choose 0, but let's say we plug x equals 0 into this red situation. So we plug in x equals 0, we solve the resulting system, and we get something that doesn't work. Likewise, in this blue situation, we let x equal 0, solve the resulting system, we get something where all the variables go away and it doesn't work. So if we think back to Algebra 1 and Algebra 2, when we solved systems of equations and we ended up with something that doesn't work, we had no solution, right? Now, the situation in this case is that we actually did something to this problem that wasn't necessarily true. We made a guess, right? We guessed that x was 0. So essentially what this is telling me is that x can't be 0, right? So ultimately, I just can't choose x equals 0 in this problem. So I need to try something else. I could try x equals 1, x equals 2, but I don't recommend doing that because you could end up on some crazy goose chase that's going to last forever. So I would try picking a different variable to be equal to 0. So let's make y equals 0 in this case. So 7x minus 4z equals negative 27. 9x plus z equals 39. So if I solve this, I might multiply the bottom one by 4. 36x plus 4z equals 156. So 43x equals 129, I believe it is. So x equals 3. Then I would take x equals 3 and plug that back in and find what z is, since I already know that I picked y to be 0. So if I plug in x equals 3, I'll plug it into this one. 27 plus z equals 39. So z equals 12. So what I end up with is a point on the graph, 3, 0, 12. Point on the line, 3, 0, 12. Now in this one, let's try y equals 0. So I have 7x minus 4z equals negative, or I'm sorry, this problem has totally different numbers. 2x plus 3z equals 72. And 4x plus 6z equals negative 11. Now if I multiply the top one by negative 2, what I'm going to notice is that all of these still go away, and this would be negative 144 minus 11. I still get negative 155. So this is a bigger issue. Like, it doesn't matter. I plug in x equals 0, y equals 0, this still doesn't work. Now if I think pretty carefully about this one, that should make sense. If I look at these two planes, 2, 4, or 2, negative 4, 3, 4, negative 8, 6, these planes have the same normal vector, right? They may be different magnitudes, but 2, negative 4, 3, and 4, negative 8, 6 are basically the same normal vector. So these planes essentially should be the same, but the numbers they're equal to don't make any sense. Like if this one's 72, I multiply the left side by 2, I can't somehow get negative 11. And that makes sense when I look at the cross product of the one on the right. the cross product is 0, 0, 0 of these two normal vectors. So basically what's happening is I can't move anywhere. So my direction vector is a non-vector. So this is the case where the planes are parallel. Doesn't matter what x is, doesn't matter what y is, I can't make this work. So these planes are parallel. Now in this case, I end up with something that does work. So I can write an equation. Notice that I had a point, 3, 0, 12, plus t, 0, negative 43, 86. Now, why did it not work when I plugged in 0? Well, it didn't work because look at what is happening with my direction vector. X doesn't move on my direction vector. So because of that, since x was 3, I couldn't have made x equal 0. X has to be 3 because x doesn't move. But for y and z, they can be other stuff because notice y moves and z moves. So if I plug in any value for t, I can get any other value for y and z. I just can't get anything else for x other than 3 because it doesn't move. So what do we do when this happens? Try something else. In this case, you probably don't have to try something else if you at least look at it and see that it doesn't make any sense. Now what happens when your value doesn't work, but it doesn't work because it actually works all the time? Like if you get 0 equals 0, we know from systems of equations from Algebra 1 and Algebra 2 that that means that you have infinitely many solutions. So I wonder what that means about x in this case. Like, does that mean that x could be anything? I wonder what would happen if I plugged in anything for x, right? So let's see if x equals 1. I mean, it makes sense, right? Infinitely many solutions. So if I plug in x equals 1, I get 7 minus 8y minus 4z equals negative 28. And 9 plus 2y plus z equals 7. So if I just simplify this stuff, I get negative 8y minus 4z equals negative 35, and 2y plus z equals negative 2. Multiply the bottom one by 4, and I add together, well, these would be 0, and this would be negative 43. So clearly that didn't work, right? So what this means is not that there are infinitely many solutions. In this case, what this means is that I chose x equals 0, and I chose very luckily. What it means is that x must be 0. So it's another similar case to the previous one, right? I used the same things, I just changed the back. So the cross product is the same. So that means x isn't moving. But if I end up getting something where it works, that means x is going to be 0. So I still have to choose something else. So let's again choose y equals 0, or I could choose z equals 0, or whatever I wanted. But if I have 7x minus 4z equals negative 28, and 9x plus z equals 7, I should know what's going to happen. Like x is going to be 0. But if I multiply the bottom one by 4, that ends up being 36x plus 4z equals 28. Negative 28. The z's go away. I have 43x equals 0. So x did prove to be 0. So now I have x is 0, y is 0, and z must be 7 after I plug in 0 for x, right? So x must be 0. Now, there's a lot of different things I could choose for y and z, but it's usually easier when you pick 0 for things. So 0, 0, 7 is going to be a position vector. Then I have my multiplier, and here is a equation of the line that works for these planes. Now what about this one? We ended up with 0 equals 0 when x equals 0. I could try y equals 0, but I'm also going to get 0 equals 0. And again, you just kind of can think about this one. Notice that if I look at these things, I really multiplied this by 2. And also notice what happened. These got multiplied by 2. So in that case, they should actually be the same plane. And that makes sense. So I'm not going to get a line because the planes are actually the same. Again, notice when the cross product is all zeros, you can't go anywhere. So you can't make a line. So these cases occur when one or more of the direction vectors has an x, y, and or z component of 0. If all three of them are 0, then it's a parallel plane situation, or the planes are equivalent. If at least one thing moves, then you end up with a line that just has a component of 0, and you have to try something else. So like in these cases, we tried y equals 0, you could try z equals 0, something like that. But you must try something else if that's the case. If you get something that's true, the variable must be what you tried. If you get something that's false, the variable cannot be what you tried. So notice, in this case, it was false. X couldn't be 0. X had to be something else, because this 0 component made it so that x doesn't move, so we had to actually guess x correctly. We couldn't guess whatever we wanted. In this case, we guessed correctly, so this x must be 0. In most cases, it doesn't really matter what you guess, but in certain situations, when you have a component of the direction vector that's 0, you either have to guess correctly or you have to try something else.